Thank you very much, Ulysses, for the introduction, and thank you very much, the organizers, for this invitation. I'm very happy to be here. And what I'm going to talk about today is a project. Actually, we have been working for a quite long time together with Benedetta Pellacci from University of Campania, Dario Mazzoleni from Pavia, and Lorenzo Ferreri, who is now a PhD student at Scuola Normale, but before was mathematical engineering at Politecnico di Milano. And actually, by now we have, we'll say, a fairly complete picture of this stuff. So I would like to describe this problem to you. You see that the problem is a shape optimization problem, and in particular in some singular perturbation regime. But the problem comes from population dynamics, so I would like to take my time to introduce and motivate what we are going to study before presenting our results. So, from the very beginning, let me start with a basic model in population dynamics. So we are interested in describing the evolution of a species, a biological species. So U is the density of the species at the position x at time t. And a very basic model to describe this is to consider a evolutive equation, a reaction diffusion equation of this kind, with a logistic, say, right-hand side, but a heterogeneous, meaning that the coefficients of the reaction term may depend on the position, and this is the most important feature of this model. You have an initial condition, of course, everything is settled on a bounded regular domain, I will be more precise later, and with some boundary conditions, okay. And first of all, what about the boundary conditions? Well, you can deal, and we will deal actually with the different ones. The typical ones are Neumann in case of, say, niche, ecological niche, or Dirichlet in case of a lethal boundary, okay, but also Robin and other conditions can be considered, mixed ones, for instance. And the two main characters of this first part of the introduction are the coefficient d. You see that I consider a very basic diffusion operator, the Laplacian, but there is an intensity, say the motility coefficient d, which is a positive constant, and m of x, which is the heterogeneous intrinsic growth rate of the population. And roughly this describes how much the habitat is favorable or unfavorable to the species. And the important thing here is that m, which in principle will be an L infinity function, say, changes sign, because there will be positivity regions which are favorable to the survival of the species, and negativity regions which will be hostile. P is just takes into account the internal competition. It will not be relevant for the moment. So what's the basic question for this kind of model? It is the long time behavior. Actually, existence, global existence and uniqueness are not an issue for this easy model. What about the long time behavior? Essentially, you can detect between two different, say, outcomes. Extinction, meaning that exponentially in time, say, that there will be a vanishing of the population, or persistence, which in principle is every other outcome. Actually, in this framework, it is not difficult to show that there is, say, persistence only if you have a global attractor, which is just a unique steady-state solution of the model. And so the question is, can we detect which of these two happens? And in principle, the answer may depend on the initial condition, and on the various parameters that we put. Actually, it turns out that the answer depends just on M, on D, and on the boundary condition. So let me show you first what are the easy, say, things that one can deduce. First of all, if the habitat is pointwise negative, non-positive, say, well, this means that the population will extinguish for every initial date. No way for the population to survive. Okay? On the other hand, in the Neumann case, if you don't have the lethal boundary, or zero flow across the boundary, then it is enough to have a habitat which is, say, favorable in average, in a sense, to get persistence, again, for every initial datum. Okay? So these are sort of the say, trivial cases, say, easy cases. What about the remaining cases, which we will focus on in the following? In the remaining cases, then the motility, the coefficient D, starts to play a role. And it happens that essentially diffusion is somehow against persistence. Okay? If the diffusion is too large, then there will be extinction. If the diffusion is small enough, then you will have persistence. And you remember I'm dealing with a, say, in the title I have a optimization problem, and the optimization will concern precisely this star. Okay, this will be the object of our optimization problem. So to describe mathematically the problem, I need to introduce a related problem. So for a moment, if you want, you can forget about the model, although precisely the very same problem that I did before. So now fix omega, which is the domain, fix m, which is an infinity weight which can change sign, and consider this eigenvalue problem. This is a weighted eigenvalue problem. You see that lambda appears in front of the weight m with the appropriate boundary conditions, Neumann, Dirichlet, or whatever. And what happens is that the previous discussion is related to the principal eigenvalue, positive principal eigenvalue of this type. What is a principal eigenvalue is, one would say, a first eigenvalue, an eigenvalue with a positive associated positive eigenfunction. Actually, it turns out that if m really changes sign, this problem has typically two principal eigenvalues. And under the previous assumption, one of them is always less or equal than 0. The other one is the one which we are interested in. So the positive principal eigenvalue, well, you can get it just with the usual radius quotient, paying attention to choose functions which have a positive integral of mu squared, because m changes sign, so you will also have functions that gives you this integral to be negative, and then you get the negative. And if you recall the discussion that I did before, what goes on is that persistence is equivalent, it is possible to show, is equivalent to this condition. So at the end, you see that the threshold D star, which is the threshold for the motility, which distinguishes between persistence and survival, is nothing but 1 over the eigenvalue. So, say, the question to arrange the habitat in such a way that to foster, say, persistence of the population, it means try to get the star as big as possible, and this can be translated in minimize the principal eigenvalue. So this is the spectral optimization problem I'm interested in. Optimization with respect to the weight, which is the description, say, of the habitat, of the heterogeneous habitat, and of course I have to decide which class of habitats I deal with, okay? And the typical constraint that has been considered in the literature is both L infinity and L1 constraints, say, so typically you have a, say, minimal value and a maximal value for the weight to be assumed, but also the integral of the weight has to be less or equal than something. If you want, this constraint is sort of the total amount of resources that you are putting inside the habitat, okay? So you are asking that this is, of course, compatible with the point one. Okay, so this problem has been investigated a lot in the literature. Now here I am putting just the references which are relevant for my discussion, but there are much more papers about. And starting maybe from these were the first papers to introduce this problem, but later it was very much considered by Berestiki, Amel, Roch, and other collaborators, and more recently you see by Lui, Yanagida, Lambolet, and so on. Okay. And let me also mention that although it is quite different from a model point of view, there are a number of related results also in a different setting, because a very similar optimization problem, sorry, I have some problem with my, yes, because a very similar optimization problem appears in the context of composite membranes. So you are trying to minimize the fundamental frequency of a membrane made up of different materials. And this is the, in this context, the result by Chaniglio, Griser, Curata, Koenig, and so on, at the beginning of the 2000s. But in that case, M is the density of the membrane. So in this case, typically, you have also a positive constraint from below, not a negative one. This is a very big difference with respect to this context, although many things can be somehow translated. So. Okay, so what do we know about this problem provided by this literature? And so, first of all, let me change, sorry, you see that here I had an M0. Let me sell this M0 to get a new parameter delta whose role will be clear in a second. And the main theorem here, proved by Cantrell and Kostner for the Dirichlet case and Louis Yanagida for the Neumann one, is that, well, there is an optimal weight, at least, say, an optimal weight, and the first order optimality condition is that the weight is bang-bang. What does this mean? It means that it saturates somehow all the constraints that you have. So you see that here, this is just the indicator function, okay? This means that there exists a measurable set D inside of omega with measure, Lebesgue measure equal to delta, which was the parameter that I put here before, so that the optimal weight is just 1 on the set D and minus beta on the complex. So actually this is a piecewise constant function with exactly the two values that are the two constraints, and this measure equal to delta is exactly the right measure to achieve this constraint on the L1 part. Another important thing is that, maybe let me go here, I have some picture maybe to illustrate. This is just exactly the very same statement that I just copied on the slide before. So you see, in any omega, you have that the weight is equal to 1 in D and equal to minus beta outside. So D is my favorable set, optimal favorable set for the habitat that I want to design. And the other property is that D can be characterized at the level of the, say, eigenfunction, because this is in particular, this weight as a principal eigenfunction, and the weight is the super level set of, say, a positive optimal eigenfunction. Okay, so this is the game that one wants to play now. Notice that this tells you nothing about D, just that it has measured delta between 0 and measure of omega. So, thanks to this result, now I can translate my previous spectral optimization problem in a shape optimization one. Okay, so now the problem is to determine D, so let me change a little bit notation. Now, the weight is always essentially prescribed by the set D, and the optimal design problem that I want to study is the minimization of the eigenvalue. Here again, you see that I put the Rayleigh quotient weight. This is just a weight, okay? And I want to minimize now among all sets having prescribed measure. Okay, and we know that this lambda is achieved by a super level of an associate eigenfunction. Okay, probably here I don't have the eigenequation, but maybe let me go back a minute to it. This is the eigenequation, okay, and now we know that M is a piecewise constant, okay. So in principle, what do we know about the eigenfunction? We know that it will be C1 alpha for every alpha strictly less than 1, okay, because you have just an L infinity right-hand side and discontinuous. And, but still, this means that at least you can always think that this super-level set, you can always take it to be open. Actually, it is not difficult to see that the solutions to this eigenfunction cannot have plateau, okay? They have level sets with zero measure, so actually you can always choose the set to be open. And the main question now is what are the properties of this d delta, okay? And this is what we studied. Before we start with our description, let me first tell you what was known before, and then essentially what was known was the behavior in dimension 1, that I will describe in a moment also to give you the flavor of what one can expect, and something in higher dimension, but for very, very specific cases. So what about dimension 1? And here, again, I have some picture to depict the result. Well, what goes on is that now you have that the domain is the interval 0, 1. The set will be a subset of measure delta. First of all, it is proved in these papers that you don't have fragmentation. That is, that the optimal set actually is an interval in this case. This is not trivial in principle because it may be convenient to split the favorable zone in more zones. And once you know that it is an interval, actually, what about the position of this interval? This is the last property that you can try to investigate. And what goes on is that it depends on the boundary condition, as one may expect. So when, in the case of a lethal boundary, in the Dirichlet case, what happens is that the best way to put resources is the most far away from the boundary that you can. This is somehow reasonable, at least, no? So in this case, the interval d delta is just at the middle of the prescribed interval omega. On the other hand, in the Neumann case, you have the opposite situation. It is much more convenient to put resources at the boundary, okay? And actually, one can investigate. You see, in this case, you are in dimension 1. The weight is piecewise constant. So actually, you can play with second order ODEs with constant coefficients, at least piecewise constant coefficients. So you can essentially describe everything. And you can also consider the Robin situation. And in this case, what happens is that you have a further threshold, say A star, for which if A is bigger, then you are exactly in the Dirichlet case. Of course, the eigenfunction will not be this one, okay? But the position of the interval will be the central one. And in the smaller case, it will be exactly at the boundary. And in the threshold, what goes on is that any interval inside is the same for the eigenvalue. Okay, so this is the situation. What about higher dimension? So higher dimension, and this gives you also the idea of the proofs. The higher dimension comes. Higher dimension essentially can be treated by symmetrization, which was the technique used also in the 1D. So what about Dirichlet? Well, Dirichlet is easy because you can use a Schwarz symmetrization, okay? And what goes on is that if you know that omega is a ball, then in the Dirichlet case, the optimal best set for every delta will be exactly a ball, a concentric ball with the right measure. Okay? No surprise, maybe. What about the Dirichlet case? Well, in the Dirichlet case, you cannot use symmetrization on disks. What you can do is you can try to do Steiner monotone rearrangements along every, say, direction. So the right domain to do this is the square, say, or an orthotop in more dimensions. And then here you see these are simulation by Rock and Hamel from this paper. And what goes on here, you see that the black part should be the D, the optimal favorable zone. And actually, you can always rearrange everything in such a way that this is, say, based on the left bottom corner of the square. Of course, you can rearrange it in any other corner on your reference. And what goes on, you see there are some sort of phase shifts, meaning that at the beginning it looks like a quarter of a disk, roughly, in the corner, okay? Then it becomes something like a strip, and then it becomes like the complement. And this also gave some, they gave some conjecture about the possibility that maybe this set has constant curvature on the boundary, or maybe that for delta small it may be a ball, and so on. And these were, let's say, all that was known before we started. So what about our results? What we did is to try to consider this now, and the natural question that one has, okay, first of all, is it true that this that fragmentation do not happen? And is it true that in case of Dirichlet you have to stay very far away from the boundary, in case of Neumann you have to intersect the boundary, and so on? And our idea was to deal with the case of a general, say, omega, not an omega with a prescribed easy shape. And also, as I said, there were also on the market some conjectures about constant curvature, quarter of a disk, or stuff like this. But actually, this were already disproven by this paper, and which says that the only case in which you can have a portion of disks is when you have the Dirichlet situation that I. Otherwise, this will never be. Okay, we deal with this problem, and of course, at least it was too difficult for us in this generality. So we didn't want to lose generality on the domains. So what we do is the singular perturbation regime, small volume one. Okay, so we investigate these questions mainly when the volume of the optimal set goes to 0. Okay, one expects concentration, of course. This has been first to formalize and then to prove it. But in particular, if you have a sort of a concentration, then you can deal with the two questions, which are where does the set concentrate and what is the asymptotic shape of this d delta. And this is actually the two questions are somehow intertwined. And this is what we try to study. Okay, so after this very long introduction, I hope it was not too boring to you, but somehow it was significant for me to become interested in the problem. Let me go with our results. Okay, so first of all, let me start with the Dirichlet case. We have, say, a full complete description, both in the Dirichlet and in the Neumann. And I start with the Dirichlet one. And I also divide these results in, say, two statements. The first part is, say, qualitative kind of results, and then I will have a quantitative counterpart coming in the next. So first of all, so remember now that d delta is the favorable zone, okay? U delta is the eigenfunction. So what we have is, first of all, that if delta is small enough, then first, U delta is a unique maximum point. And in particular, this implies, remember that d delta is a, maybe let me depict. D delta is the super level set of my function. So if you have only one local point, local maximum point, this means that whatever happens, the super level will be a connected set. Okay, so this will be, say, my U delta, this will be omega, and then here I will have my d delta optimal set inside of omega. Okay, this is the situation that one expects when delta is small enough, and in particular we can answer to the question about connectedness and non-fragmentation. And second thing, actually, we know by the results by Lambolet, Lorenzo, then and Privat that this set cannot be a ball unless omega is a ball. That is the very easy case that we don't consider if you want. But still we can prove that somehow it is almost a ball at the limit, okay? Meaning that it is a nearly spherical set in the following sense. Okay, so d delta is radially diffeomorphic to this shrinking ball. So you see that now x delta is the maximum point. So here you are writing a sort of a polar representation of the set. And you see that, well, R1 is just the radius of the ball of measure 1. So that with this delta 1 over n in front, you have a ball of measure delta, okay? But you have a defect, say you have a asymmetry. And, well, first of all, this asymmetry, you see, and here happens one thing that I will discuss later, it is C11, okay? And when delta goes to 0, you have the answer to the two questions before. What about, well, the second one is easy to read. The asymmetry goes to 0. So essentially, it is asymptotically a sphere. But maybe more interesting, what about the point of concentration? Well, this x delta, which is the center of the candidate sphere, goes to a point. And this point is a point which maximizes the distance from the boundary. So you get exactly what you had in the, say, 1D case. Okay, so this is the result. So maybe let me go on with some comment about this. So first of all, okay, this is just what I said. For small delta, it is the set is connected and it concentrates at point maximizing the distance to the lethal boundary. And actually, this statement maybe is quite, it contains a description of all what I said, but it doesn't contain the real theorem that we prove. And the real theorem that we prove is a sharp asymptotic expansion of the optimal eigenvalue. This is how you prove this result. You have, remember, lambda delta is the eigenvalue depending on delta. What goes on is that this eigenvalue blows up. And blowing up, you have to develop it, and essentially the first order development will be responsible of the first part of the statement, and the second order development will be responsible of the second order term, saying the development will be responsible of the 3 and 4 here. And I think I will have time to tell you some more about the strategy later. And this is very nice because we were stuck a lot in part, well, in several points in this trial. It took years to get to the end. But one very helpful result was by Maria Soria Caro that I met for the first time during the coffee break. So I'm very happy now that I can cite this. This paper by Caffarelli and Maria and Pablo Stinga. And then a later refinement by Dong about transmission problems. Why I'm mentioning this? Because, as I told you, the optimal regularity that you have for the eigenfunction is C1 alpha, alpha strictly less than 1, okay? On the other hand, remember, the delta is a super level set. So the boundary of the delta is a level set of this function. So if you just apply implicit function theorem, what you can expect is C1 alpha. You cannot expect C1 1, okay? But we can use the connection of this problem to transmission problems and the very nice regularity results in these two papers to improve this to C11. This is an important part of our strategy, and also, in turn, it gives you also something that maybe was not completely expected for general omega, that C11 convergence actually gives you strict convexity of the delta for delta sufficiently small, okay, because you have the R1 part which is dominating, okay. So, in a sense, we get also that not only connectedness, but convexity, even if omega is not convex at all. Okay? Here, omega is any Lipschitz domain connected. Doesn't make a problem. Okay, not only this, but C11 convergence helps a lot in going on with a more precise description of the optimal set. So now let me go with the quantitative part of the results, but before I forgot. Let me also say that the very same kind of description can be done actually taking a slightly different center of the ball, that is taking the barycenter of the delta instead of the point of maximum, okay? Since this is an asymptotic description, This is not something very strange, say. But this is important because this helps to go to the second part of the statement, the quantitative part, in which I would like to get more about this decay of the symmetry, phi delta, and this can be done using a quantitative estimates, okay, for the problem. And what goes on is that, okay, we know that in C11 it just vanishes, but if we consider a slightly less, say, alpha less than 1, so a slightly weaker norm, then the decay is quantitative. So we can see that the decay is of exponential type in the volume of the. Okay. Now, to do this, you need to take the right concentration point as the barycenter of the delta. Why? Because this is related to a counterpart, which is this rigidity result that we prove for the corresponding problem in Rn. Okay, so now in a second I will go probably to a description of our techniques, but you may imagine, since I have a small volume regime, the natural thing to do is to do a blow-up procedure and to work in expanding omega with one volume sets. So what about this problem? Well, actually, you can get a corresponding problem on Rn. Okay, so an habitat which is the full Rn with a positivity region with measure 1 and a negativity region on the complement of it. One can see that actually, although Rn is not compact, you get first eigenvalues and so on. This is not very difficult. And the rigidity result is this one. So if you take any nearly spherical set, in the sense that I described before, center, say, at the origin, with bounded C11 norm, and barycenter 0, because clearly translation, this problem is not translation invariant anymore, so this is the role of the barycenter that you need to rule out translations, and measure 1, then we have this sharp estimate about the L2 norm of the asymmetry. Okay, and on the one hand, we know a lot. Clearly, we apply this to our eigenvalue problem, rescaled eigenvalue problems. And since we have an exponential estimate here, essentially, we have an L2 estimate, but also a vanishing of the C11 norm, and so by Gagliardo-Nire, by interpolation. And interpolation, actually, you end up with this kind. Okay, so I think, if I remember well, yes, this is all about the Dirichlet part. So let me go to the Neumann one. Okay, so now for the Dirichlet, we have concentration at points which maximize the distance of the boundary. What about Neumann? We expect that the relevant stuff happens at the boundary. So here, actually, this is a more, say, disrupted kind of statement because it is scattered in different papers, but I summarized it here in just one statement. So Neumann case. First of all, this resemble, it is very similar to the previous one, so I highlighted in red the different parts that are worth to be commented. So first of all, when delta is small, again you have a unique local maximum point and then connectedness of the region. But now the maximum is not inside omega, it is at the boundary. It doesn't tend, it is at the boundary for delta sufficiently small. So in particular, the delta is connected. And moreover, then the set now is not anymore really nearly spherical. It is rather the intersection of a nearly spherical set with the boundary. At this point, what goes on is that in the Neumann case, you will have some points, and your set will be somehow, okay, now I'm drawing it not convex, but it should also be convex. They say the interior part, at least for delta sufficiently small, although I have not stated this yet. And one important thing is that, so not only it touches the boundary, but it has a big intersection with the boundary, okay? So you get the counterpart of the 1D situation. And what about the rest of the statement? What about the, well, still you have the C11 convergence to 0. What about the point of concentration? And what one discovers is that the best point to concentrate are those that maximize the mean curvature of the boundary. And finally, also in this case, we can have a, say, quantitative decay estimate. I wrote just the L2 because lazy somehow. But you have seen from our results that the L2 part is the one that comes more naturally. And actually, in this case, the concentration is much slower. Okay, what we can prove is just a decay of a polynomial order in this case. Okay, while before it was exponential one. Also, this somehow is expected because here the boundary has a relevant influence. Okay, in the other case, the concentration happens very far away from the boundary. So, this can be expected. And of course, from this, you can get all the bounds in C1 alpha, but the bad problem is that actually interpolation of exponential are exponential, interpolation of polynomials are polynomials with very bad exponents. So I didn't brought. Of course, here you will have an exponent depending on alpha, where alpha is the power. So once again, now you have a connected set concentrating at points with curvature. So actually the first part of this result, say not really the first and second, but a first version of this statement without the final information. We first get it in a couple of, well, in one older and one more recent paper. And the second part, which is essentially the location, the exact location at point of maximal curvature, it is more recent, also in collaboration. Okay, so some comments, some mixed comments. First of all, again, to have the quantitative part of the concentration, you cannot center your description exactly at the point, the maximum point, but at something which somehow is a sort of a projected barycenter on the boundary of the delta. It is a bit technical, but not very unexpected. And what about the regularity of the domains? The part, the Dirichlet part, essentially you need no assumption on the boundary. Okay, so Lipschitz say enough, but probably you can even use weaker assumptions. Here the boundary plays a role because here, as you can imagine, big part of the work is flattening the boundary, reflecting and stuff like this. So you need a regularity of the associated diffeomorphisms. So in particular, the first part of the theorem, say up, yeah, exactly. The first part requires C2 theta boundary, but the last part, when you try to do the quantitative part, then you need some higher regularity to deal with this. And okay, this is the exponent that I didn't want to show you, but this is the right rate of decay in case alpha, decay C1 alpha. And you see that, of course, this degenerates. Okay, so maybe a few words. How much time do we have? Because I'm a little bit lost. Ah, okay. So I will, finish before. So what about the strategy? So actually, probably I don't know if this is famous in maybe in the free boundary community, not very much, but this is the strategy is based on a series of papers very famous in the, say, nonlinear analysis, variational method framework. And indeed, if one knows this, probably this is something that one can guess, because in these results, these are a series of papers started from Nie and Takagi, and then also Wei, and then Delpino, Fellmer, and a lot of other people came out in this setting. These results concern concentration for semilinear elliptic equation, so the framework is a bit different. So the concentration problem is this one. Okay, you see that here you have a concentration parameter epsilon squared in front of the Laplacian, and you have a u power p. P is bigger than 2 and say less than the sum of the critical. And what about these papers? Well, what goes on is that essentially, depending on the boundary condition, you get very similar results to those. And we somehow mimic the same strategy. So what is the strategy? First of all, you need to understand what is, you need to change scale. You see that here I have no volume constraint, but in a sense, if you wanted to reabsorb this epsilon, the right way is again to make a change of variable for which the new domain is expanding, okay? So at the end, you expect that any limit problem you get from here, but also for our problem here, is obtained expanding a domain, so in Rn or Rn plus, or maybe a cone if you really are on Lipschitz domain. This depending on the point on which you center your blow-up procedure, because if it stays inside the domain, you will get Rn. Otherwise, you will see the boundary, or better, some tangent cone at the boundary. Okay, say Rn plus, just. Especially because you will never see the boundary in the Dirichlet case, you will see it only in the Neumann case, where actually I assume C1 much more than C1 for the boundary. So detect the associated problem, and if you are lucky, the associated problem is not just a limit of the scaling, it's also a limit of the variational structure. So here you are interested, or in our case, you are interested in minimizer of some problem. You get a problem in Rn or Rn plus, for which you still have a variational structure and a minimizer. And then once you have this, you play the game of competitors. So then you take the problem in Rn and you blow down it to get a competitor for the problem in omega. On the other end, you take your problem on omega and you do something, a blow-up procedure, to try to go to a, say, a competitor for the problem in Rn. This is, say, roughly the strategy. And this can be done, actually. I think that maybe I can describe this, but I will go quickly on it. So the limit problem, essentially, somehow I already introduced it, because it is the one that we used for the quantitative part of the results. So this is the problem. At the end, you need to deal on Rn with a weight which is 1 in some set A of measure 1 and minus beta on it. Okay, so nothing very much has to be said about this, apart from the fact that you know everything about the final eigenfunction, because this is explicit in terms of Bessel function. So you have a very precise description of it, and essentially the important thing is that this eigenfunction decays exponentially at infinity, and this is why we get exponential decay in the point. And then, okay, these are very ugly, I will skip it, and then you can use this problem to try to bound the optimal eigenvalue from above and from below, and here is the description. You see that in the Dirichlet case, the expansion of the optimal eigenvalue, you have a blowing up power delta minus 2 over n, and then you have a first term of the development, which is just a constant related to the problem on Rn, and then the second term, and you see that in the Dirichlet case, here you have exactly this d star, which is the distance actually of the blow-up point, and then you see that it is convenient to do this very far away from. And okay, you have some difficulties with respect to the semilinear elliptic case, but I think that I can really skip about this. So let me stress instead maybe a second about the quantitative part, okay, and where the C11 estimates come up somehow. So you remember in the qualitative part you still had this description in phi delta. So what's the point here? The point is to get the C11 regularity. And how do you do this? Actually, this is not probably difficult once one has the results that I mentioned before. These results are about the transmission problems, okay? So what goes on here is that our eigenfunction is C1 alpha, say, across, okay? And we consider the derivatives simply of our eigenfunction. They are C1, so you can with no problems. And what one gets is that the derivatives satisfy a transmission problem across the free boundary. So what we need is, first of all, a C11 regularity, and this is granted by the papers that I mentioned. Actually, this paper is done in the framework of Laplacians, while this is written for more general divergence operators, so we need it when we use diffeomorphisms to flatten the domain and stuff like this. The real point is that we need a uniform estimates of this type because we need the phi delta to be uniformly C11 in order then to pass to the limit. Okay, so this is somehow something that one needs to do, but again, working with diffeomorphisms and looking closely to the proofs in this paper, we are able to get a sort of a uniform result for the transmission. Okay, very good. So this is how we get. So this is exactly the previous slide, and I think that about this maybe another comment which may be of some help in this audience is that actually this is the say rigidity result in Rn, okay? And one thing that may somehow seem strange in a sense is that here we have a control of the eigenvalue with respect to the optimal one, which is in the ball, using the L2 norm of the spherical asymmetry. While maybe you know there is a long history about this kind, and the strategy we use is the Fugile, the typical one. Okay, essentially we expand, we try to write the map that associates to the set the eigenvalue and to expand it in some sense, in some way. Okay. Here, what goes on is that, in principle, this has been done for a lot of situations, in particular by Brasco, De Filippis, and Velichko for the, say, Faber-Cram problem for the lambda 1 with, so in say, A with 0 Dirichlet boundary conditions. And actually, the asymmetry always pops up as a H1 alpha norm, okay? Well, what happens here is that essentially this is a sort of a two phases problem, because you have an equation inside and another equation outside with the discontinuity across. And what comes up is that it seems like the natural norm for this asymmetry would be the L2 rather than H1 alpha. Actually, we can show that this is sharp, so this seems to be. Okay, so this was essentially the last thing that I wanted to tell you. Open problems that we are working in a lot, but by now we have a description just for delta small. We would like to have something for delta maybe very big or delta fixed, but it's not very clear how to deal with this. You don't really have a problem on Rn. Something which would be doable is Robin boundary conditions, because for the semi-linear elliptic case there are papers that treat this. Currently, we have a strategy about this, and it would be interesting also, I think, to deal with this with non-local diffusion, which make very much sense in the context of biological models and population dynamics. But here, of course, blow up is not a tool that you really can use, so in the non-local setting, so it is not very clear how one can proceed. Okay, so I think it's all. Thank you very much.